The Made Public Cyber Manufacturing Platform consists of an open-source manufacturing data infrastructure, BEMD, Biomaterials-Based Electronics Manufacturing Data Infrastructure. This platform is empowered by artificial intelligence and machine learning algorithms, basic designs of electronic devices, and advanced designs of electronics. There are two modes of access to BEMD. A basic mode that allows everyone to access basic designs of electronic devices, and an enhanced mode that allows for modest fee-based access to advanced designs of electronics. The generated fees will be used to license additional advanced electronics designs to make the platform self-sustaining. Users would select an electronic device design and print the bio-based electronic device, which could be sensors or batteries, using bio-based inks, the user-friendly cyber manufacturing interface, and accessing a home printer if the printer is affordable. Otherwise, the user could access a printer through a nearby public library, a printing service provider, or a value-added retailer. The project will explore the fundamental science to enable precision growth of plants as source materials for bio-based inks, efficient extraction of plant components for ink production, bio-based ink formulation, printing electronic devices, active learning of the above three processes, and energy-efficient and environmentally benign eco-manufacturing of electronic devices. Through our efforts, we will enable a community of innovators, including students and the public, to convene and reimagine eco-manufacturing. Made Public will spark innovation for the next generation of manufacturers.
What we're going to focus on here is going essentially from the plants to extracting the nanomaterials and kind of setting up Thrust 2 for next time.
As Stuart mentioned, what we're doing is growing plants and then taking that biomass that the plants produce and extracting components from that. And so the two sort of primary materials that the plants produce are cellulose and lignin. And different species produce different concentrations and amounts of those two components, but some plants like Brachypodium are model species, which means that we can genetically engineer them to have different chemical structures. And so Brachypodium is a C3 species, so unlike the larger bioenergy grasses, it has the C3 process of photosynthesis. But the reason that it's a model species, the key features are shown in this table. It's small, it has a really rapid life cycle, and most importantly, it's relatively easy to transform this species, meaning you can manipulate the genes in it to produce different components.
This slide is showing, I don't know how many of you actually seen this miscanthus. You saw, I think you had seen this kind of grass in your backyard, garden setting, but this miscanthus giganteus, which is a very tall stature warm season grass, is a perennial. Most of the grass we work with is a perennial because a perennial has much more efficient and stress tolerant.
He's kindly ground them up for us already, but we grind them up. We do some base washes, and the main purpose of the base wash is to remove the lignin, and you end up with a sort of alkali lignin from these base washes. So a couple of that base washes there. We then expose it to some bleach that removes any of the residual sort of lignin and starts to remove some of the hemicelluloses there. And then essentially, at this point, you're essentially at pure cellulose. We do an acid treatment. That acid treatment is to dissolve away the amorphous cellulose I told you about. And this is what leaves you with this is what you get at the end of this after it's acid hydrolyzed. If we use HCl as the acid, then you get these uncharged nanocrystals. These things are not dispersible at all. What we do here is you actually do a tempo. This is an oxidation process that selectively oxidizes the primary alcohol here to give you a carboxylic acid. That's what these are. These are the cellulose nanocrystals that we get out. These are the dimensions that were actually measured by small angle neutron scattering data. So you see they're longer and they're more rectangular than the wood. So again, major differences between the CNCs you get from wood and from MXG here. From about 200 grams of the stock, we get close to 80 grams of the nanocrystals. which is pretty close to kind of the cellulose content that we get out of this. If we don't use, the acid here is actually important, what acid you use here. If we use sulfuric acid, you actually go straight to having sulfated CNCs. So these are sulfate half esters on the surface. These are directly water dispersible, and they're roughly the same size. Here's a TEM of them that we get from those. We have worked with argon. Argon has actually scaled up our process into the kilogram and ton scale. So we're now, this is what I'm saying, we've now gone from the lab to the scale up process. So now this is an industrially viable process thanks to the materials engineering research facility at Argonne.
From our perspective, thrust number 2 is all about receiving bio-derived raw materials from thrust 1. This would include cellulose nanocrystals and lignin-derived graphite. We would then take those, fashion them into electronic inks, and then hand those off to thrust 3, where there would be efforts in developing printed electronics and sensors based upon those inks. So what we do in our lab for the last several years is so-called liquid phase exfoliation of 2D materials. And how this process works is we start with a bulk layered material, for example, graphite. We would then put it into an appropriate solvent. We would typically add some sort of exfoliation aid, which could be a surfactant or a stabilizing polymer. Introduce some sort of shear force, and we'll talk about how we do that in a minute, but it could include methods like sonication, and it could include methods like shear mixing, or what we're doing now, so-called wet jet milling. And this would peel away or exfoliate the individual layers or few layer flakes off of the bulk layered crystal. I'll note that this exfoliation process is imperfect. By that I mean less than unity yield. And as a result, the next step is to perform some sort of purification to tease out the thinnest, largest area flakes from that which is poorly exfoliated. This traditionally has been done with centrifugation, which is a bottleneck in our process. And so a key goal of this program is to move to continuous flow methods like cross-flow filtration and hydrocyclone-based separations. If we're successful, we'll then be able to scalably produce liters, gallons, and beyond of conductive inks, which we can then use to print devices in a scalable manner and ultimately enable large-scale manufacturing. Now, I will note that we've been developing these inks for a while, particularly the graphene inks, and I'll tell you a bit more about that incumbent process. But a key component of inks are their rheology, which includes their viscosity. And we've been able to tune our viscosities by a few orders of magnitude. And this allows our inks to be compatible with a wide range of printing methods, including methods like inkjet, aerosol jet, screen or gravure printing. We can also have spray coatable inks and blade coatable inks. And that's, I think, one of the key advantages of our methodology compared to many in this field is that we worry about everything, including rheology. And that's, of course, critical to getting the optimal performance in your printed structure.
We are going to support thrust 1 in terms of monitoring different parameters for growth of plants, including physical and chemical parameters, such as temperature, oxygen, and light condition, humidity. And then the nutrients, if we grow this in water, then we would be able to monitor nitrogen, phosphorus, potassium, boron, etc., that are critical to the growth of the plants. And then obviously, in order to print these devices, we would need to use inks derived from thrust 2, and then also looking into understanding of the printing process, in collaboration with thrust 4 and 5. Thrust 4 will be helping us to model and optimize the printing process, and then thrust 5 is mostly looking at the lifetime of the sensors and batteries and their energy consumption and material use, the environmental benefit or impact as a whole manufacturing process.
In-house, we have inkjet printing capabilities, gravure and rotary screen printing capabilities, and then some of this laser-induced graphene. We have a laser engraver that can convert polyimide into graphene. I'll show some of those results as well. We're working on converting, or also using that as a annealing technique, and it changes the surface wettability and electrical conductivity of those electrodes. So of course, interfacing with Thrust 2 here with the Hersham group to get those bio-derived conductive graphene inks, working with Zhonghoon to print and make the sensors.
This one, we want to go through the basics of what we are trying to do in data simulations and machine learning for eco-manufacturing, and combine the CT4 and CT5 to thrusts that looks at connecting plants, feedstock, extraction, formulation, and printing of electronics. So there's myself, Shantanu Chaudhary, Wei Chin, Yuxin Chen, Rebecca Willett, and Jennifer Dunn all are present.
In Thrust 1, the major inputs are the things you can change, include like things like what plant to grow, and nutrition, humidity, temperature. Those are we call the process variable. And through experiments, we can identify the volume and the quantity. And the outcome or deliverable from this thrust is basically the CNC and Legna derived graphene. And this information will be passed to the next slide. So Thrust 2 will take that material as well as its own inputs, for example, the process variable I just talked about, like including choice, for example, solvent. You can choose different kind of solvent. And in this thrust, we foresee there will be both experimental data as well as simulation data. And using the methods I mentioned briefly earlier, we can assess the yield, waste, the quality, and the deliverables is the bio-based inks. And this material will be passed to the final thrust, thrust number 3. In this case, we have a set of printing process variable like ink viscosity, speed, and those we can change. We also have post-processing variable that we can design for. And this thrust, again, we think involve both experimental data as well as simulation data that Shantanu has talked about. And we can use similar methods to predict the objective. In this case, will be the spatial resolution and the device variation. And all this will come together at the system level. So at the system level, we have production cost, recycle biodegradability, energy assumption. And this is where the thrust 5 will also play an important role in order to assess, all those parameters. So we kind of foresee this is the thrust 5 will really come in at this integration level. So this is a kind of just a kind of a simple extraction of what we think the interactions. And in order to kind of facilitate the convergence on what are the major important variable or data or attributes should be included, we kind of think some like a formal methods such as knowledge graph can play a role here. So here I show example, just using the thrust 2 as example. Like you start from, it's like a mind graph, like we call mapping, right, between different entity in the system as well as the attributes that you think important. So for electronic printing, that leads us to think about we're using graphene and the wet jet milling, and then the wet jet milling and the graphene can all has its own attributes, and there's some kind of causal relationship we can draw in using this diagram.
In order to get something useful, right, we need to actually play with the system or massage the parameters, trying to figure out the best tunable configuration of the system. And usually that exploration requires interaction with the real environment, requires real action and monitoring and computational cost. So what we're trying to do is kind of figuring out what are the intrinsic complexity during this optimization and learning process. We're trying to adaptively build up the system such that the algorithm or the experimentation cost eventually is comparable, for example, with the best algorithm that one can ever design idealistically. So here I listed kind of five different thematic area that we're currently exploring, and we see pretty well docking to this current project. The first one is, imagine that we're trying to build a simulator or emulator of the real world system. Like if you think about trying to simulate the printing process from all the trainable and fixed parameters to the target outcome. For example, to map from like the ink pattern and the particle size of the printer to the final like conductivity and roughness of the film, etc. Right? How do we like efficiently build a computational system that can accurately and faithfully reflect the performance of real system while being able to represent the data in an efficient way that is tailored for optimization?
These are the research questions that we're looking to address in CT5. Many of you will recall when we talked with our program manager at NSF, they were really interested in this project being a sort of a concept or proof of concept for eco-manufacturing and circular manufacturing. So there's an opportunity to have a leadership role here in defining eco-manufacturing and how we quantify what that means and what its benefits are. And then there's a angle there in terms of communicating with policymakers and consumers so they can learn about products that are made through eco-manufacturing. Within the project itself, our main role is to evaluate the cost and environmental effects of the sensors and batteries we're producing and made public. And we really want to also understand if we were to develop this technology and it became disruptive, how might sensors and batteries made from bio-based and recycled materials disrupt the electronics supply chain? And finally, we want to look at the sustainability benefits of distributed sensor manufacturing because that's what we're proposing to do within Made Public.